Welcome to this explainer. Today we're jumping right into the ultimate tech showdown, the transition from classical computing to quantum computing. Now, right off the bat, we need to get one thing straight. This isn't just a step up in speed. It's not like simply slapping more RAM or a better processor into the devices we use every single day. No, this is a massive, fundamental paradigm shift in the actual logic of how machines process information. We're talking about moving away from the predictable, everyday world of binary code straight into an architecture totally governed by the mind-bending rules of quantum mechanics. And frankly, understanding exactly how this shift works is absolutely crucial if we want to grasp the future of tech.
Okay, to really understand the shift, we kind of have to look at the foundational architecture of the conventional computers we rely on. Think about your laptop, or even the most powerful supercomputers operating today. They're all built on classical binary logic. You've got millions of these microscopic transistors acting as tiny switches, just constantly flipping back and forth between a 1 and a 0. And hey, it's an incredibly efficient system, for sure, but it's inherently sequential. A quantum computer, on the other hand, operates on entirely different physical principles. I really want to emphasize this. We aren't just talking about a faster, more optimized processor here. We're looking at an entirely different species of machine, built from the ground up to solve problems that classical architecture literally cannot handle.
So, to truly grasp the massive gulf between these two architectures, I want you to imagine a totally impossible task. Picture having to find one specific grain of sand hidden somewhere on one of the beaches on Earth. Just think about the sheer physical scale of that search mission for a second. You've got vast stretches of coastline, massive dunes, and endless oceans of sand. If we assign this ultimate search mission to a classical computer, it absolutely has to follow its foundational programming. Because it operates linearly, it's forced to painstakingly check every single grain, one by one. It picks one up, scans it, realizes it's not the target, puts it down, and moves to the exact next grain. It's a strictly sequential process, and therefore it's fundamentally bound by time. And here's the kicker. Operating with this linear method, it would take a classical computer literally billions of years to complete the search. It just completely hits a brick wall. This is such a vital point to understand. It doesn't matter how much you upgrade the RAM or how aggressively you scale up the classical hardware, we are bumping up against the physical limitations of Moore's law. Because a classical processor is forced to evaluate one possibility after another, there are certain complex mathematical problems where the universe would effectively end before a conventional machine could compute the final answer. The bottleneck isn't the speed of the hardware, it's the sequential nature of the logic itself. But this is exactly where quantum architecture rewrites the rules of the game. A quantum computer doesn't just speed up that linear process of checking those grains of sand one by one. No, it bypasses that linear constraint entirely. By leveraging quantum mechanics, the machine evaluates every single grain of sand across every single beach on Earth in the exact same instant. It takes a problem that requires billions of sequential steps and effectively collapses the whole shebang into a single computational moment. Pretty wild, right? But to understand how a physical machine is actually capable of achieving this level of simultaneous calculation, we need to peek under the hood at the underlying physics. The main engine driving this crazy capability is a rule-breaking scientific principle known as quantum superposition. Now, in classical computing, as we know, the foundational unit of data is a bit, which is strictly binary. It's either a 0 or 1. But quantum computing uses what we call qubits. And because of superposition, a qubit isn't locked into being just a 0 or a 1. It can actually exist as both and in multiple states simultaneously, right up until the exact moment you finally measure it. When you link a bunch of these qubits together, they create vast, sprawling possibility spaces. So instead of navigating a maze by walking down one path, hitting a dead end, turning back, and trying another, a system utilizing superposition effectively walks down every single path in the maze at the exact same time. To put that into perspective, it's kind of like deploying a billion assistants across parallel universes. Each assistant checks a different grain of sand instantly, and then they all merge their answers back into our reality to hand you the exact location. And listen, this isn't just some abstract thought experiment. It has profound real-world implications for us. Those grains of sand, they represent the unimaginably complex variables found in nature. This is exactly why quantum computers are poised to completely revolutionize fields like molecular modeling, material science, and drug discovery. When you're trying to simulate how a really complex protein folds or how a brand new pharmaceutical compound interacts with the human body, you're essentially searching through billions of chemical combinations. Quantum architecture can navigate those massive possibility spaces instantaneously. So what does this all mean? Well, we are literally standing on the edge of an entirely new era of computation. The leap from classical to quantum isn't just a simple evolution of the tools we already have.
It is a fundamental disruption of what is computationally possible. But that immense power also brings up some massive questions about the infrastructure of our modern world. Think about it. Most of our current cybersecurity, the algorithms protecting everything from your banking data to national security networks, relies on mathematical problems that take classical computers billions of years to solve. If we suddenly unlock a billion parallel universes of computing power, what happens to the digital locks that protect our world today? Let us know in the comments below if wrapping your head around quantum superposition just broke your brain.